All right, hello. Following up where we left off in the last video, we were looking at these two new rules that we have for differentiating. Helps us do this process a little bit faster in a lot of cases when we can use them. Previously, we looked at the product rule. Now we're going to look at the second one that I've got on these slides, the quotient rule. So reminder, products are a math way of saying multiplying two things together. The product of two numbers is whatever. Same thing with functions, whatever you like. So a quotient is when you have a division. So we're going to look at functions that are formed as a function divided by another function. So continuing our two additional rules, like I said before, we had the product rule. Now we've got the quotient rule. So we use the quotient rule when the function we want to differentiate is the quotient of two functions. Again, just think divide. So something maybe looks like this. We've got a function that perfectly reasonable function on its own, but we can kind of view it in terms of smaller functions making it up as this function quadratic divided by this function, that linear one. So that's what we're saying here. We can think of it as y equals 2 minus x squared and y equals 4x plus 1, where we look at the quotient of that by that. The reason we do that is because we're going to introduce a rule that allows us to handle differentiating these types of functions where we know the numerator, which we do, we know the derivative, and we know how to differentiate the denominator, which we do in this case. So we would use this rule because we don't have a rule, at first glance for this big function as it is on its own. So you kind of look at the parts that make it up and then look in our toolbox of differentiation tools, and this is the one that we would use. So we want to introduce this rule. Just a reminder, we won't go through the example that we did with the product rule, but it's probably not the one that we would expect. We might guess that if you're differentiating f over g, you might guess that it's the derivative of f over g, and that's 100% wrong. So it is a little bit trickier, kind of like the product rule. There's a little bit more to it. So let's look at it. So here's the quotient rule. Start off, we need to have two functions that we know are differentiable. These are kind of the ingredient functions, the smaller functions, the whatever you like. They make up this function that you're looking at. So you got something where it is a quotient of two functions that you know about. You know how to find the derivatives. In practice, you would need to know how to find the derivatives in order to use this, but even if you didn't know how to find them, this statement is still true. So that quotient is going to be differentiable where defined. This is a little wrinkle. We didn't focus on it with the product rule because we do have the problem here where you don't want to have a division by 0. But we'll see that in just a second here. So there's our formula, and letting you have a minute or a second to kind of take that all in. So this kind of Leibniz notation, looking at the rate of change of this function with respect to x, so the derivative, it's the derivative of f times g, so the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator. They sometimes might describe this a little bit different in different textbooks. I know our product rule in the textbook that we use is written differently than how I write it. I like to, whether it's f times g or f divided by g, I like to go fg, and keep that kind of common structure. It's easier for me to jump back and forth whether I'm using the product rule or quotient rule. I feel like I have just a little bit less to be forced to memorize. With the product rule, you can switch things back and forth because you're adding two things, and a plus b is the same as b plus a. Here you've got a difference, you're subtracting something, so you have to be careful with the order. If you got this term flipped with that term, you'd be off by a factor of -1, so you got to take care when you're doing that. So derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, and then we got to remember to divide by the original denominator squared. This seems kind of crazy, and it's maybe not clear why it works. Probably shouldn't be clear why it works at first glance. Our textbook goes through a proof. You can follow that. It's worthwhile to do so. We're never going to ask you a question about proving it. But it doesn't come from nowhere. It makes sense, and you can follow the proof, and you can see why it works. But just looking at it, it does seem a little weird. We're worried about remembering the formula and using the formula, so we're not going to go into the proof, but it's worth checking out and seeing if you can work your way through it. In that prime notation that we also often use, we'd have f divided by g. That function, its derivative is f prime times g minus f times g prime. Again, exactly what we have up here, just with that slightly different notation. And then, of course, divided by g squared. Okay, so quick example. Well, we'll see how quick. Compute the derivative of f of x equals 2x over x to the 3 halves plus 1. I know this derivative. I know this derivative. I don't know the derivative of this whole thing. If I had a formula, I would just use it. But I don't. I know these kind of parts that make it up. So that's why we're going to use the quotient rule, because all you need to know is what's the derivative of the numerator, what's the derivative of the denominator. That's the information we need to use that formula. So that's the reason why we have it. Alright, so we tried to color code this a little bit to make it a little easier. Numerator in blue, denominator in red. Remember, the formula tells us the derivative of this is going to be the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, and all that over the denominator squared. So derivative of 2x, and derivative with respect to x is 2. Derivative of x to the 3 halves plus 1. Here you'd use the power rule. It's 3 halves x to the 1 half plus derivative of a constant 0, so that's all we have there. This is perfectly okay, but if you want to clean this up a little bit, this is a little bit nicer. This idea of what it means to simplify. It's not a well-defined thing. One person's simplify might be another person's complicate, whatever that even means. There are some things we can agree upon. This is a little bit cleaner. It's somehow shorter, more compact than that. So we would probably say this is nicer, like I said there. But this is not a it's not 100% clear in all situations what simplify means. Nevertheless, if you can kind of clean it up, it's often worthwhile doing, especially if you're going to do something with this. If we're going to find something like f double prime, the next derivative, working with this is nicer than starting off with this one up here. So it's worthwhile kind of cleaning it up when you can. Whoop. So real quick, that's it. That's the rule. So we want to do a lot of practice on our own, getting used to it. Let me write this out, and then we'll, like you saw on the slide there for a second, see what it is, just to confirm. Now I've got f's and g's here. Don't get tied down by the names, right? So in the formula we said f and g. Just think numerator and denominator function. So the name doesn't matter. But the order and how everything fits together does. So I'll take the derivative of the numerator, which is 2x, times the denominator, minus the numerator, times the derivative of the denominator, which is just 1. And I'll still write it there this time. All over x minus 1 squared. Perfectly fine here, but this is one that's not too difficult to clean up. I'd have 2x squared minus 2x minus x squared all over x minus 1 squared. And so that looks to me like x squared minus 2x all over x minus 1 squared. If you like, if you find it easier, you could take that a step further, factor the numerator, look like this. I don't know that this is that much simpler than that one. If you're going to differentiate again, you might leave it like this, because here you'd be using the product rule. But both pretty clean, both pretty simple, so we'll leave it at that. For this second one, again, we're using the quotient rule. Take the derivative of the numerator, that's negative 1, times the denominator, x squared plus x, minus the numerator, 4 minus x, times the derivative of the denominator, which is 2x plus 1, all over x squared plus x squared. Again, nothing wrong with this. A little cumbersome, a little crowded, complicated, whatever you like. If you're going to use it and start evaluating and trying some different values of x, so maybe you want to clean it up, but this is perfectly legitimate. We'll go ahead and clean that up. If I distribute that negative, I get negative x squared minus x, and here I would get, I'm a little pressed for space, so I'm going to kind of do two things at once. 4 times 2x is 8x with the negative, so minus 8x. 4 times 1 is 4, so minus 4. Negative x times 2x would be negative 2x squared, but that negative's out in front, so plus 2x squared. See if I can squeeze this in. Negative x times 1 is negative x, the minus of plus x. Barely squeeze that in there. Maybe I'll combine terms. 2x squared minus x squared, we'll call it x squared. Negative x plus x cancels. Negative 8x is what's left. Minus 4. Doesn't look like a clean, nice factorization there, so I'm not going to try to pursue that any further. This looks like a pretty nice, nice form to end with. Alright, so basically we just want to get that formula down. You want to commit it to memory, get used to it, using it a lot, so it's just kind of second nature. Again, we're not worrying about the proof. We want to be able to just do this process, and then we can start doing more problems or reuse it, but we got to get this method down. So real quick, here's what I ended up with. X squared minus 2x over 1 minus x squared. Looks good. X squared minus 8x minus 4 over x squared plus x quantity squared. Looks like we did it right. Alright, so that's the second of the two rules that we looked at over the course of 2 videos. Starting to get a little bit more complicated. We're looking at the product of 2 functions, how you can take the derivative of a function that you see as the product of 2 functions, how you can take the derivative of a function that you see as the quotient of 2 functions. Those kind of ingredient functions, you need to know how to work with those, otherwise you can't use this rule. But typically, you would know how to do that. For this example, polynomial, 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 everything's good. So this is the quotient rule, and that's it for this video.